Oh, all right. So again, good afternoon. My name is Sunday Kanshaw, and I'm the managing partner of Fleissen. Thank you for joining this webinar this afternoon. And now I will go quickly through the profile of our speaker this afternoon, Mr. Lincoln Austin. He has 25 years of experience in instrumentation and specifically for flow measurement in the process sector. Mr. Lincoln started his career at Foxborough, Yozel in the Great Britain as an apprentice in a mechanical department, or they started as mechanical technician. I think over the time he has also supported the company to invent some DP transmitters. Later, what is called A13, 13A and 15A pneumatic wells. These meters usually work pneumatically, so basically means that they don't require power. They only require air pressure to work. So he then moved to study materials and microstructural engineering at Sheffield and qualified as an engineer, B.Eng Hans. After the degree, he started a company specializing in flow technologies, covering electromagnetic flow meter, vortex, turbine, thermal, clamp-on, ultrasonic, and others. Basically, he has worked with almost all the metering technologies you can think of. He recently started a company called DP Flow, look after differential pressure DP flow metering in the process and chemical industry, where there is declining skills based as other flow technologies predominate the sales push from manufacturers. So basically, you can see these days ultrasonic is coming strongly. Coriolis DP meters are beginning to get quiet, but they are still very good. Of course, so DP Flow has a huge remit of instrumentation and more, and now looking after the spares and replacement of Daniel Junior and Senior Orifice. So if you want any spares part as regards to Daniel Junior and Senior Orifice assembly, then DP Flow is a place to go with the dual chamber fitting and associated auxiliaries. DP Flow is an approved agent of Schneider Electric and EMCO Controls, and other agencies can be found on their websites. We are partnering with DP Flow. So if you need any support in the Nigerian market, we can support you to get reached to DP Flow and give you all the support. Well, ladies and gentlemen, having gone through Mr. Austin profile, we want to inform you that if you have any question during his presentation, you can place those questions in the Q&A section. If you want, and if it's about any other information, then you can put that information in the chat panel. At this point, may I grab the indulgence of everyone to ask Mr. Lincoln Austin to start his presentation. Mr. Lincoln, over to you.
Thanks very much, Sunday. Great introduction. Hopefully you can all hear me okay. And please feel free to put something on the chat if you need us to stop or have a question. Sunday will audit those and ask questions for you, so we can stop at any time during that presentation. So today we are going, and thank you, Sunday, for that great introduction. Yeah, that's very good. Thank you. What we're going to do is, as Sunday has published, is we're going to talk about the influencing factors in primary metering, differential pressure metering systems, predominantly on Orifice plates and Venturi tubes. But a lot of the issues that you can find also apply to others, such as nozzles, cone meters, and wedge meters. So a lot of the issues that you'll find are fairly common. Some aren't, but yeah, we shall see. So I'll just get the presentation set up. Let me just share my screen and give me a second. So if I share my screen. Hopefully that is now sharing. And Sunday, can you see my screen okay? Am I sharing all right?
Yes, I can see your screen.
So you should be able to see this screen here.
Yes, I can see it.
So as I say, it's we're going to cover influence quantities in DP metering installations. So as somebody said, I'm actually ex-Foxborough, did my mechanical apprenticeship there in the 80s, and I was there. So some of you may still find in some of your applications, you might have some pneumatic instrumentation that runs on a 3 to 15 PSI signal rather than a 4 to 20 milliamp. If you're familiar with those sorts of signals, which I'm sure you are. So that's my background. Then studied metallurgy and have fallen back into the sales and support role within instrumentation. As Sunday said, the spares side, so if you've got any Daniels carriers, the dual chamber, senior or junior orifice fittings, the spares and spare orifice plates, the seals, things like that, that's problematic. So we're doing a supply on those. And also there's some software that we also do that is sizing for orifice plates and Venturi tubes and cone meters. It also does and is heavily dependent on valves. So if you're interested in that, talk to Sunday and we can get some information to you. Right, so on to the presentation. Influence quantities in DP metering. DP metering, in my view, is relatively straightforward, but a lot of people think it's one of the magical arts, which it isn't. It's just other technologies have also pushed through, and you know, they're much more reliant on electronic processing and things like that. One of the things I'd always say with differential pressure metering installations is if there is a problem, there are ways to find it. Whereas with other technologies, in my view, you may find that actually you've got to call the manufacturer in, and then it's all built into some electronics. So you know, it's more difficult to resolve. It's a fairly loose statement, but something that you can pick up on as we go forward. So who are we? 20 to 30 years in instrumentation, founded 2013, specialising in DP, evolved to supply a wide range of instrumentation technologies reflecting our overall experience in the industry. And I started at Foxborough. This was the original plant. It's not there anymore. Most of it's now moved out to the US. Typical applications that we cover: liquid gas and steam, oil and gas, upstream and downstream, wet and dry grass, crude, drilling mud, subsea applications. We do things like activation air for wastewater treatment plant, biogas and biomethane plant. We can measure flows from pressure ranges in thousands of bar to vacuum, temperatures from -268 to over 900 centigrade. That covers things like helium, oxygen flows, all those good things. And some very, very low flows up to millions of standard cubic feet a day, as you'd expect in the gas sector. So just to touch on, I know we've got a number of people attending today that are very interested in the gas side. So we supply a lot of kit into the gas distribution network here in the UK, and also on the upstream gas side as well. But after processing, when it's going down to the process plant, we deal with the distribution companies rather than, from our perspective, the custody transfer point. But that custody transfer point is changing as we can see. So just a little bit on the flowing bores, since we're concentrating on orifice plates today. We can go from 0.5 mil, which is very, very small, up to 15 meters. So that's pretty wide range of pipe sizes and flows. The contents, what we're going to do today is cover the measuring principle of the primary devices. We'll be very quick on that because you should have a good, decent knowledge of that, I would guess. The primary devices we're going to look at are typically going to be orifice plates. We're going to look at the piping side, so straight length, carrier sizes. We'll look at the pressure taps, where they should go, what size they should be, what the effective burrs are. or the orifice plate itself in this section. So we consider things like edge roundness, deformation, what happens if you install an orifice plate backwards, so beveled plate facing the flow, what happens with eccentric bores. We'll then look at the Venturi tubes. So again, we'll cover piping, the straight length, the upstream carrier ring installation issues, meter geometry. So that's going to cover things like orifice plates and Venturi tube, what happens if you get the geometry wrong, piezo ring effects, the entrance and oil coating and surface finish on Venturis. And then we'll look at the pressure taps on the size and the burrs. We'll then start to head towards the back end of the presentation. We'll look at impulse lines. This is a classic area of issue. We'll look at the sizes and lengths that are used, what joints and tubing's used, and where some of those issues are. And then we'll just touch on secondary devices, which are things like differential pressure transmitters, flow computers, where the uncertainty can lie, and data entry on things like flow computers. So very basic. We're not going to stay on this page for very long, but just to give you an understanding, the operating principle is based on the Bernoulli's equation. For what we're talking about today, it's a circular pipe fully contained with a fluid, i.e. it's not partially full if we're talking about liquid, and with gas it's dry. This is for a single phase fluid, so again dry gas or 100% liquid with slow changes in flow rate, i.e. non-pulsating, coming off a pulsating pump or something like that. And the way this works, it revolves around putting a restriction in that pipework. And as you can see on the drawing there, you've got the upstream on the left, the downstream on the right. As the fluid comes down the pipework, it's forced through a restriction. The velocity has to increase. And as you can see on the graph below, to maintain the continuity and conservation of mass, the velocity has to increase with an associated decrease in pressure as you go through that restriction, and then you get some pressure recovery as the velocity slows down again. So all primary devices, that's orifice plates, Venturis, pitos, nozzles, wedge, and cone meters, essentially work from the following equation. That is, on the left, mass flow rate, Q for flow, M for mass. You've got a discharge coefficient, a beta ratio, which is the ratio of the pipe bore to the orifice bore in the place of the orifice plate. You've got an expansion factor, that's the epsilon you can see there. You've got your pipe area, pi d squared over 4, and then your square root function, within which lies your differential pressure and your density. That's the equation, and essentially how it works, just so that we're all on the same page. So onto orifice plates. The ISO standard says that the straight length for a given beta ratio must be as per their table. So we're using ISO 5167 here. So if just looking at that table, we've got a 0.6 beta ratio and an upstream 90-degree bend. It says you need 42 pipe diameters, as you can see on the table there, which is obviously quite a long installed length. If you're just looking at column A, if you're happy to add a little bit of uncertainty, you can go to column B, which is 20D. And the point of this presentation, or one of the things that I want to talk about, is when you go to site, what happens if you don't have that straight length of pipe? How do you relate what your performance is going to be from what you discover on site? So what we're going to do is rely heavily on some engineers that did a lot of research at the Foxborough measurement company. I'll reference their text at the end, and we've extracted a number of tables and graphs from that text, but that's freely available. We'll give you the ISBN number as well at the end, so that you're free to research it. So just looking at that then, for example, 42D or 22D, if we've compromised it, we've got 13D and 9D if we're looking at the 0.6 and 0.5 common beta ratios for an orifice plate. excuse the image, it's straight out of the Miller book. But if we just have a look here, so here's our 90-degree bend. If we look at the previous slide, so if we're looking at a 0.5 beta ratio, just on the far left there of that table, where we've got 22D and 9D. So here's our beta ratio table. Beta ratio goes across the top. What happens if we've actually got 4 diameters from a 90-degree bend, and we can just use that table to give us an idea of how that performance is going to be affected. So if we were just using that table before at 0.5 beta ratio with a 9D inlet, that sort of lies between the 8 and 10D. We're looking at probably about a 1% error. But if we've got a 4D before the inlet, you can see that actually, where a lot of people would say, oh, we can't use this installation, there is some research and table data available from the Miller research text that allow us to ascertain, well, we're not going to be 30 or 50% out on our measurement. We're actually probably going to be about 2% out if we've got a 0.5 beta ratio, maybe slightly more, but perhaps 2.2%. That can help, especially if you've got a large installed asset and changing all your pipe work is prohibitive. That then allows you to fall back and come to some agreement with either your process manager or your gas supplier to actually loosen up some of that uncertainty limit if your pipe work's been compromised. It's not so much of a problem on smaller pipe work where you've got perhaps 1, 2, or 2, 3, 4 inch, because you can relatively easily extend that. If you've got a large pipeline, 12 inch, and you need to put 42 diameters of 12-inch pipework in, that's taking up a lot of real estate and should be done. But what do you do right now if you find you've got your pipework compromised? So you can start using this sort of table to give you some idea of where errors will lie. And of course, always refer to ISO 5167 as your primary point of reference. So now we can start looking at other effects. So we have a double bend here, and again, looking at that 0.5 error. If we've got 40, it's actually not too bad. We're looking at an additional less than 1% probably. Again, this is all for engineering discussion between the gas supplier and the end user. Or if you're in process, it's you can make an engineering decision based on some of these tables. So here you've got 2 elbows in the same plane upstream of an orifice meter, and if we're looking at the pipe diameters, PD is your pipe diameters of 4D, your beta ratio is going to sit at about, according to the test data here, about 0.75% additional error. And so we can move on. So the table on the left is flange tap and corner tap set of test data, and on the right we've got a radius tap. So that's 1 diameter upstream is your pressure tapping, and half a diameter downstream is it for the downstream pressure tapping. That's the table on the right. So on the left we've got the corner tap and flange tap. Again, just using that 0.5. So obviously some of the data is quite limited, but if we use the 0.5 with 40D with 2 bends out of plane, we can see we've got an additional perhaps 0.75% to apply as a correction factor. But if we're 4D, your office plate is 4D downstream of a double bend where the bends are out of plane, you can see actually we've got a additional 3% error there or thereabouts. So it could be that a lot of people consider the orifice plate to be much further out than that, but it looks like we've got some reasonably good performing flow meter from what could be, according to the standard, a really compromised installation. So, there are other things you can do. We do them, as does other manufacturers. You can put in a multi-hole plate. So that's a plate that conditions the flow and measures at the same time. So it looks like a conditioning plate. So a conditioning plate typically has, 20 holes in it of different sizes at different locations. A multi-hole conditioning orifice plate will have 4 or 5 holes in it, and it has an additional uncertainty associated with it, so it's probably going to give you 1 to 1.5%. If you look at this table, a standard orifice plate with 0.5 beta is actually only going to give you 3% error, so it's pretty good in relation to it. And as you increase that beta ratio, things tail off. They start to look quite good, and then all of a sudden they drop off the other end. And of course, some of this data is outside the standard. We've got some table data here for beta ratios of up to 0.8 as a beta ratio. And you've got the table on the right for your radius taps. So sorry about the quality of this image. And so we've got perpendicular planes here with a spacer in between. So the others were closely coupled bends, whereas here we have a spacer between the first bend and the second bend of between 5 and 11 diameters. And you can see the effect there. 0.5 beta ratio, there's hardly any effect at all. But there's, with a 0.4 diameter inlet, we're probably still only 0.5% error. I mean, that's a really tolerant measurement in my view. And again, as your beta ratio increases, you start to end up with a bigger error. And again, so you've got 3 perpendicular planes here, and as you'd expect with the swirls, would normally start to follow the inside of the bend, so you can get the direction of the swirl. We start to really see some big effects here. So with 40 pipe diameters on a beta ratio of 0.75, that's very forgiving, but at 0.5, actually we can see some compromises here. If we're at 10 diameters, we've easily got a 6% error, and if it really goes off scale once we shorten that. So close coupled bends, you can really start to see you really need to be cautious in terms of what engineering data you take from it. So that's your 3 bends out of plane. So you can really see how pipe geometry influences your measurement. Regulators, partially open valves, things like that. There's another table. So we've got for a beta ratio of 0.74 with 20 pipe diameters. That's right in the middle there. Not too bad. So fair tolerance for beta ratios of 0.5 and 0.7. But as you get close to 5 pipe diameters with globe valve upstream, if you look at the bottom left-hand part of that chart with a beta ratio of 0.7, you're starting to see errors of 5, and that's tending towards 8% error. So as soon as your pipe diameters increase, things improve. With partially open valve, a beta ratio of 0.375, if you look at the middle part of that graph, it says 0.375, so that's a really starting to get quite a small orifice within your pipe work. You can see that partially open valve will really start to influence things as well. So important to keep tabs on that. Again, the quality of these pictures, we'll give you the reference at the end. You can buy your own reference book that will give you all this data. It's a very good reference book to use, so I would strongly recommend you get it. Here we've got, if you've got an orifice carrier, so I'm not talking about the Daniels carriers, I'm talking about a carrier that will fit within or between 2 flanges. So let's say here, I'll tell you what I will do quickly. I'll just quickly bring up the standard. And Sunday, can you see the standard in front of you on the screen at the moment? Just want to check that's showing, or are you just seeing the presentation?
Yes, I can see
it.
ISO 51672.
Yeah, okay, right. So this is the Orifice standard, and just so that we're all on the same page, I'll just scoot through this a minute, just so we can see. So here's a carrier, for example. And the next slide just talks about, this is a carrier with annular rings that are built in, and on the same drawing we actually show a corner tap device there. So this is the annular ring. here. And what we're going to just talk about is if this carrier that sits, this is your pipework here on the left. I don't know whether you can see the mouse pointer there.
Yep.
You can, excellent, thank you. And with this Orifice carrier, what happens if this actually protrudes into, i.e. the carrier is too small for your pipework? What happens if this protrudes into the pipework? So that's what we're talking about here, and you can see the carrier now is protruding into the pipework. And for this set of test data, this is where the carrier ring has a beta ratio of 0.9, i.e. on a 100 mil bore pipe, the carrier ring is actually 90 millimeters, so it's 5 millimeters smaller around the edge of that that pipework. And you can see and it's also related to the thickness of the carrier as well, called the X space. So if we had a pipework 100 mil bore and the carrier ring was 90 millimeters with an X space, i.e. the carrier ring was 40 mil wide, looking at that bottom curve there, you can see the beta ratio of the orifice, the effect of what that carrier ring has on the additional uncertainty of that measurement. And again, at 0.3 beta ratio, it's fairly inconsequential, 0.5%. But as you go to 0.5, you're starting to see 1.5% error, and just follow that curve all the way around to the right-hand side. If you've got a beta ratio of 0.7, a carrier ring that is too small can start to have effects of around, well, here we've got 5% in this set of test data. And looking at the upper graph, that's if you've got a narrower carrier ring of 0.2, 100 mil bore, the thickness, the X space is 20 millimeters rather than 40, and that follows the upper curve. So it gives you some tools with which to assess the effect of that measurement within your process, whatever that process may be. Right, so that's a little bit about installation of the installation of an orifice plate. And next we're just going to talk about the pressure taps. So we'll just get everyone on the same page here as well. On the right hand side we've got the corner tap, that right hand side drawing, and that corner tap demonstrates what's called an annular orifice. So that carrier has an annular ring that goes around to average out the pressures. The bottom part of that same drawing shows single point orifice tappings. And as we go to the drawing on the left, you can see at the bottom we're demonstrating flange taps. You can just see that there it says L1D and L2D. That's the flange tap arrangement, and radius taps are shown as L1B and L2C, and that is 1 pipe diameter upstream and half a pipe diameter downstream. That gives you an idea of what we're going to be talking about next. So the tapping diameter for radius and flange taps. So Reader Harris, if you've not come across him, he's done a lot of a lifetime of research really at the NEL laboratory in East Kilbride in Scotland, and he's done some tests and reports that the tapping diameter has little effect on the bias induced in the measurement, so long as the tapping is correctly located. So in tests on turn 3-inch pipe, comparison between the ISO tappings of 2 millimeters and the API standard 9.5 millimeter tappings, no noticeable difference was made. I think that's a really interesting statement there, because if you're looking at an ISO installation, you're like, hold on a minute, the tapping diameter within the pipe work is outside and bigger than what is stated on the ISO standard. Well, the API and the ISO are tending towards agreement, so those tappings can potentially be bigger even though they're not in compliance with the ISO 5167. That gives some confidence of where your measurements are going to line. It shouldn't really affect your measurement. So if you've got some errors, that's probably not the place to look at this stage. You might want to look somewhere else for some issues if you've got them. excuse me, within the ISO 5167 standard, the permissible errors for location of the upstream and downstream pressure tap for flange taps are up to 0.606% for the upstream location and 0.018% for the downstream tap. Testing outside these limits has not been researched here. So equations do exist for correction of the pressure tap location for radius taps. And I've said there, see Reader Harris for further details, and I've got that reference for you at the end. So just to put that back into context, here's the drawing, and if you look at the left-hand drawing and the bottom part, those are your flange taps. So you can see how critical it is to make sure that those pressure tappings are in the right place. Don't deviate. Now, I guess that's very controllable with a flange tap anyway. So, yeah, that's something to bear in mind if you're getting a local machinist to put those tappings into some flanges for you. Just be careful. It's very critical, and if they don't fit right, I haven't really got any test data to tell you how far out that will be. And in actual fact, if you need us to, we can go back to that drawing that I showed earlier of the way the vena contractor works for, not work, but the shape of it. So with that flange tap arrangement, the tapping location is crucial because you don't want to be one side or the other of that vena contractor. Otherwise, your measurement is going to be out. We just burrs on the tapping. So burrs can have -30 to +30% bias on the effect of the measurement. If a burr exists on a tapping where several tappings exist, i.e. if you've taken 4 tappings around your orifice plate, and look at that drawing if you can in the bottom right hand corner. So we've got an orifice or a flange tap arrangement where we've got 4 tappings on the upstream and downstream side. If one of those is burred, then the effect of a single burr is mitigated somewhat by the triple T arrangement. And if you look at that drawing on the right hand side, you can see that a triple T involves you commoning up all those tappings so that they become one tapping, and that helps to mitigate any burr effect. But you know, a burr on a tapping is really, you need to think about quality of control when you're machining these. That's really what you want to be looking at. So quality control during production and inspection. Quite often people are tapping their flanges once they've installed them. Well, you need to also think there that you need to be able to have access to the end of that flange once it's welded on. If you've then tapped it, you need to be able to inspect it, perhaps carefully run a finger around the inside just to make sure that there are no burrs. And if you do have a burr, that tapping needs to be square and sharp edged. So it needs to be square. So you don't want to use a deburring tool to take that off. You're going to have to find another way to take that off. That's down to the machinists, and I'll let other people advise on that. But you don't want rounded edges on your tappings either, and you don't want burrs on them. So that comes down to machining, and it's a little bit out of mechanical production these days. So you need to look at that with your machinist. Edge roundness. So the edge sharpness does have an effect on the discharge coefficient. In the chart above, a 0.1 millimeter roundness on a bore of 100 millimeter has a 0.5% change on the CD value. So ISO 5167 states the upstream edge G shall be sharp. It shall be considered so if the edge radius is not greater than 0.0004 little d. So that's 0.004 of your orifice bore, and that's for orifice sizes greater than 25 mil. And if that requirement, that requirement is generally considered to be satisfied by visual inspection when checking that the edge does not reflect a beam of light when viewed with the naked eye. So that's a fair and easy statement, isn't it? You can check your orifice with under an inspection lamp If the edge doesn't reflect any light, it's considered to be sharp edged. If the diameter of the orifice is less than 25 mil, visual inspection isn't sufficient and you actually need to measure it. There are ways to measure it. An ingenious way recently came across at an inspection lab is to use some lead solder and just knock it onto the orifice edge using a like a nylon, I call it nylon hammer, but just to create and get a profile of that orifice edge, and then you can inspect it under a shadow graph or something like that, which is fairly easy to do with an inspection company. But edge roundness does have an effect. If you've got dry gas or 100% liquid, you know, that orifice isn't really going to wear, in my view, unless you've got sand or wet gas or anything like that. So that's when things and problems start to occur. The plate must be flat when installed. Considered flat when the slope between a straight edge and the plate is less than 0.05, and then you've got the equation, i.e. is less than 0.5%. Fully bent plates, which hasn't been defined, I'm afraid, in the text that we're referring to, can have around 10 to 18% on the discharge coefficient. Now, plates can get bent, and if you shock them, i.e. you've got a depressurized line, and then you open your valves up and you let that water or gas or whatever it is hit that plate with the full force, you can bend your plate, and it's not great. In the whole scheme of things, what you want to know that the plate is right, because you don't want to be in a position where you're not sure whether you're under reading or over reading. You just want it to read right, because then you know, if you're paying for your gas, you know that you're paying for the right quantity, and that's the key. You don't want to induce uncertainty, because it could go against you and it could go for you. So it just needs to be right, and then you know exactly where you are. Now, this is quite common. Orifice plates do get installed backwards. It's not great, and you know, care should be taken to make sure that people install these the correct way around. And what people used to do, if you're familiar with conical plates, I'll just see if I can pull that information up a minute. Just give me a second, just so that you'll know what a conical plate is. Right, I think it's in this stand here. Give me just a second. Okay, so here's a conical plate. Here we have a bevel on the upstream side, but there is a cutout, and there is the downstream edge has been rebated slightly. So you know, this is a 45-degree angle, and what people have done in the past for an orifice plate that's been installed backwards that has a chamfer on, 45-degree chamfer on the back, is they've used the discharge coefficient for a conical entrance plate. Doesn't actually really correlate. So I'll just read this. If a bevel plate is installed backwards, errors of 18% can be expected. Miller suggested that using a discharge coefficient of 0.734 as a CD value, conical entrance, can be used. But it's not quite true. In actual fact, conical entrance plates are very limited in their scope, their beta ratio range, and the size of plate you can use. So Reader Harris suggests there's no real agreement on the CD value, as the bevel angle needs to be taken into account as well. So the bevel on the rear of a plate isn't always 45 degrees. I can't remember exactly from the standard. Oh yes, no, I'm looking at the wrong one. So I think it can be anywhere between 35 and 60 degrees. Everyone uses 45. Don't quote me on that range of bevels on the rear of a plate. You need to check the standard. We can have a look if you need us to in a minute. I can't remember it off the top of my head. That's why Reader Harris is saying there's no real agreement, because on a standard plate it might not be 45 degrees, it might be 30 degrees, and then you change the discharge coefficient. So a plate that's installed backwards, you know, don't rely on that discharge coefficient. What you need to do is take the plate out and put it back in the right way round. Okay. And as it says here, the value comes from the conical entrance plate. The reverse plate is insufficiently represented by a conical entrance characteristic. So we'll move on to the next slide. Excuse me, apologies. A bit on eccentricity here. So the orifice plate, if it's not installed, so up on the right hand side, and you might not be able to make this out too well, but actually that drawing, and again the text will reference it for you, but that plate is installed and it's in an eccentric fashion. So if you just look at the bolt holes, they're hard up against the bolts on the right hand side, but the bolts on the left, you can see there's a gap which has introduced some eccentricity. So for a 1/4 inch offset away from the tap for a 0.41 beta orifice, we can see you can have an up to 2% error. Now that actually is related to a particular pipe size, but you can see the graphs down below again, which haven't come out very well on the slides, but you can get them on the text, and these books are readily available. You can see how that that discharge coefficient is changing with eccentricity. So really worth getting this text that I'll recommend at the end. So now just pause for a minute whilst I catch my breath. Any questions? So that's the orifice plates, and you might find there's a good point just to pause for breath and ask a couple of quick questions on influencing factors on orifice plates. Sunday, are you there?
Great. Yeah, I'm here. So while you catch your breath, there is one question from Ami. You can see it in the Q&A box. Can you see the question?
Let me have a look. Sorry, I'm looking at the. Hold on. Just give me a second. It's not showing on my screen. No, you're going to have to read it to me. I can't get to it. Sorry.
Okay. So Amin is asking, what about measurement diagnostics and bias detection?
Diagnostics. Okay, so I think what Amin is referring to there is there are various diagnostic tools out there that give you bias detection that will automate that for you. That's not what we're talking about today, but is a great tool. If you can get that installed, again, Sunday, you and Paul can talk about that in more detail. And that is absolutely available. Excellent tools for detection of that bias, and would be highly recommended. So we're just talking from the absolute basics at the moment in terms of what those effects are. And as an engineer, if you're on site and you're walking around, you know, what can you look at and what can you see that would stand out as a potential measurement problem. But great question, and I think that diagnostics tool that I think Amin is referring to, if client can put that in, then do so. And again, Sunday, that's something that you and Paul can discuss in more detail.
Yes, good. So Adel Hamid Said is asking, for the orifice, what is the influence of the flow profile and viscosity on the reading of the meter? Right.
Okay. So what I'll do, because you can still see my screen, but I can't see the chat.
So he's talking about the influence of viscosity and the flow profile.
Yeah. So flow profile we've just gone through, which is all those installation errors with that pipe work, all those pipe work geometries. So single 90-degree bend, 2 90-degree bends, and 3 90-degree bends. That all incorporates the flow profile. Viscosity is also covered by the standard. And if I just whiz down to the bottom of, so here, of the standard, can you see the standard okay, Sunday?
Yes, I can see that.
Great. Okay, thank you. So viscosity is viscosity and velocity work through the equation to give you what's known as a Reynolds number, which some of you will be familiar with. And the orifice plate is one of the most forgiving and versatile measurement devices, in my view, that you can get. So for a standard square edge orifice plate, the discharge coefficient is related to Reynolds number, which is a function of viscosity. And here you can see that for corner tap, so this is the corner tap table straight from the ISO 5167, the discharge coefficient for a Reynolds number of 5,000 gives you discharge coefficient for a 0.1 beta ratio of 0.6. So it's all related and all researched. So viscosity does have an effect, and that influences the Reynolds number. And so if you're sizing, and again, if you need some sizing software, we do that. If you're sizing the plate, you really need to be looking towards the discharge coefficient. There are, if you've got flow computers on site, they should be automatically picking the discharge coefficient. If you've got, let's say you're measuring methane, for example, and you know the temperature and pressure of it and the differential pressure, the flow computer will then pick the relevant discharge coefficient. Let's say you've got a, just so as it fits on this this screen at the moment, let's say you've got a 0.3 beta ratio. The flow computer will actually pick the relevant discharge coefficient for that measured or calculated velocity, and then it will then correct for it. So viscosity has an effect, but you put that back into the equation and it then gives you the relevant discharge coefficient. So great question. Hopefully I've answered it. If not, then the standard covers it, and I would strongly refer people to back to the standard. Anything else before we? No. Sunday, just let me know you're still there.
Yes, I'm here. Yes, I didn't hear your question. You look
okay,
like
that's
breaking.
So is it breaking up a little bit? The
Can you hear me?
yes, I can hear you.
Great.
Can you hear me?
Yes, I can.
Great. Okay, I'll carry on then. I'll carry on.
Yes.
Okay. So we'll just have a shorter run through the Venturis because I see time is pushing on. So we're about halfway, but we're okay for time. The next slides that speed up a bit. So we've got the straight lengths for the ISO 5167 for the Venturi tube, and these are a lot shorter. Venturi tubes are a lot more forgiving. And so again, we've got the same sorts of tables that we have for the orifice plates for the Venturi tube. So for a single 90-degree bend, 0.5 beta ratio, we've got 9D inlet. But look, you know, you can actually have a 3D inlet on a Venturi tube for only a small percentage increase of error. So let's see if we can see some of that. So here's our 0.5 beta ratio, and here's our pipe diameters. And you can see that you know, there's very little extra effect required for a 0.5 beta ratio Venturi, but then there is quite a lot of geometry, and that conical inlet to a Venturi tube also helps condition the flow, which is why it's a great device, but it has a much longer installed geometry. Here we've got two perpendicular planes. And for a 0.8 beta ratio, as you can see that bottom curve, it starts to have a fairly significant effect, but it is only about 1.5% at a 12D pipe diameter. Pipe D straight 12D straight length of pipe for a 0.8 beta ratio. The smaller the beta ratio, the more forgiving the inlet geometry is. We've also got dimensions here of the reducer upstream of a Venturi. Again, pretty forgiving. We're looking at about an extra 1.2%, something like that. If we look at the 0.8 beta ratio, if we've got a 0.45 beta ratio, it's pretty negligible, isn't it? There's virtually nothing to it in terms of extra error that you're looking at. And if you just follow that that picture above that table, you can see we've got our reduction upstream, then we've got a straight length of pipe, and then we've got our pressure tap along Venturi. So we've got an expansion joint, obviously we're expanding out, then we've got a straight length of pipe, and then we've got our Venturi restriction. Apologies about that set of data that says 0.8. That's not all 0.8 as a beta ratio. The 0.8 is the poorer curve, by the one with greater error, and probably 0.45, that one that is very close to zero additional uncertainty. But that's the upstream piping effect for an reducer, and in this particular case, it was in joint. Got the same thing for Venturis and nozzles. Carrier rings have the same sort of effect. I won't go through that again, but again, you can see that it's populated, so you do have sources of information you can rely on if you've got a nozzle in the line. And Venturi geometry we'll go through. The radius of the cone to the throat misalignment can elicit about a 2% bias. If you've got a piezo ring that is irregular or corroded, that can elicit around a 1% error. So if you remember our triple T arrangement for the Orifice plate, on a Venturi we'll typically use a piezo ring. So that's just where all the upstream tappings are commoned up, and all the downs and all the throat tappings are commoned up. So here, if we've got an irregular or corroded piezo ring, that can elicit about a 1% error. If the entrance to the Venturi is corroded, you can get some distortion, 2% error. If you've got oil coating on the Venturi or the nozzle surface, that can offset the discharge coefficient. If the surfaces are aged, you get geometric changes like pitting, rust, and general changes with age. You can get a 2 to 2.5% error. And things like step change in the cylindrical throat, you can imagine that's going to cause a problem. Or if you get a slight expansion in the Venturi throat, that can give you a 1% error as the gas is expanding as it goes through the high pressure, the low pressure tapping. Tapping size of burrs, so you get positive bias on if you get a larger tapping, and burrs, again, here we've got big errors if you've got a burr on the tapping. I put questions, but I think we probably can push on some days. I appreciate time is pushing on a bit. If I just move swiftly on to things like impulse lines effects, and then through there we've got a quick Q&A bit, and then we've got the proper question and answers towards the end. So impulse lines, sizes and lengths. So impulse lines, aka or also known as gauge lines, lead lines, pressure and different tubing, is what we're going to be discussing next. And it's good to note that people really get this part wrong. So if you have any measurement issues, definitely check your impulse lines first. Take a quick look at the standards for the installation of the impulse lines to see how it's supposed to be installed. So sizes and lengths, rule of thumb, keep them as short as reasonably possible. They may need to be pressure tested or hydro tested, and they can have different specifications and codes to the main process piping. That's because they aren't actually, they're much smaller and have different properties. If they're less than 6 millimeters, air and liquids, depending on the media, i.e. if you're measuring air or measuring liquids, may have difficulty escaping. The bore should be generally at least 10 millimeters, but not exceed 25. Now there's a slight deviation to that, and we'll just see that in a minute. So here's Annex A from the standard. This is the guidance on pipe diameters for long impulse lines. If you've got water or steam or dry air and gas, then your transmission length, where it's less than 16 meters, should be between 7 and 9 millimeters. If you've got wet air or gas, it should be 13. Oils, 13, or very dirty fluids, they should be about 25 mil or 1 inch. And if you've got longer than that, that allows you to get a decent response time. But if you've got longer lines than that, in order to mitigate things like viscosity effects in your impulse lines, you need to increase your impulse line size. So Then if you're going 16 meters to 45 meters, you should be looking at the 10 mil bore, 13, 19 and 25 as a pipe bore. With wet air or gas, you've got risk of condensation. So that's why I've got 13 mil there on the wet air or gas instead of 7 or 9. It just eases the escape of water. It's imperative the impulse lines are installed without leaks. Use good quality tubing and fittings like swage lock or an equivalent. Follow the manual, make sure you get some training on how to install them. Follow the standards, use the minimum possible number of fittings, use a tube bender as opposed to joints and fittings to reduce leak paths, and install tube in lengths as long as reasonably possible without an extra joint. Protect them and insulate them from uneven heating and cooling. So if you are an exposed site, you don't want one of those impulse lines being preferentially heated over the other. They should be at the same temperature so that you don't end up with different densities in the impulse lines, which can then affect the measured differential. That really is going to be more important on liquids than gas, but nevertheless, they should be wrapped together or at least very close to each other in proximity. All lines, if you've got horizontal lines, make sure they are all sloped. So you don't want 90-degree bends. You want a nice slope on there with at least an 8% slope. That will help condensation to run out of the pipework. If you're on gas, always slope your impulse line back to the process, never to the transmitter. And if you're on liquid, you want to slope the transmitter needs to be below the line, and those lines need to slope up to the process. So if the transmitter's below, you don't want horizontals, you don't want any U-bends, you want it to slope up to the process. So gas, if there is any in the liquid, will naturally stay in the process and not collect in the transmitter. I've got some diagrams of that in just a moment. Excuse me. Typical rated pressure for swage lock impulse tube is in the order of 200 to 300 bar for 8 to 12 mil, and that is material and specification dependent. So check your tubing and your fittings, and tends to have an actual burst pressure when under test of about 900 to 1,000 bar. Check the manufacturer's data sheets for the actual rated pressures. Design factors are typically 4 to 1. When you're installing them, you need to consider things like access. So if your pipeline is at high level, you don't really want your instrument technicians going up to calibrate your transmitter, then sometimes people drop them down to ground level. So you really need to pay attention to how these are installed. So if that tech needs to get the valve manifold for calibration purposes, it's not always practical to install that impulse line. It's not always practical to install the transmitter close to the Venturi or Orifice plate. Think about the area in which they're going to sit. Is the area hot or cold? Have you got preferential heating? Could you get different densities in the impulse lines, creating an offset? You could get solar radiation on one line and not on the other. And you can get wind chill. You might get freezing if you're on water. And that can potentially, one, it will block your line, and the other is you might get one blocking, the other one's still operating, so you can get problems from that perspective. If you're on gas and you've got water collecting in the line because the impulse line measuring liquid, and it was 2.54 meters above the transmitter, and you had a 10-degree difference between the water-filled impulse lines. So maybe one impulse line is next to a boiler and the other one is further away. You can get over 0.5 millibar pressure difference that's independent of the transmitter calibration or the flow. And when you're measuring turn down on differential pressure meters, that can be significant. So it's really important. If in doubt, tie them together, wrap them together. If you're not on a steam application, and just make sure that they're close to each other, so they're at the same temperature. If you've got condensing gases, not vapors like steam, impulse lines shall be sloped minimum of 8% up to the transmitter to ensure that the transmitter is self-draining. So that means your transmitter is above the pipeline, your transmitter is sloped back to the process. If you see any horizontals, and there's a lot of them around, it makes them look good, but actually it's incorrect as an installation if you've got horizontal impulse pipe work. So, you know, short lengths are acceptable, but, you know, on big power stations where you've got tens of meters of impulse pipe work, it's a problem. It really can be. So you do want slopes on there, not horizontals. We've actually had installations of people walking across the impulse lines to get to an application. That's a big no-no as well. You don't want them exposed, you want them protected, as they are your measurement principle. For liquids, impulse lines shall slope down to the transmitter to ensure they are self-venting. So I've been over that a couple of times. I think you get the idea. So here's a typical line diagram for gas. So the transmitter on the left is item number 1. Then we've got typically a 3-valve manifold. It's not shown there, but 2, 3, and 3B is typically a 3-valve manifold. Not always, but could be. And then you've got the process connections 5A and 5B. That shows your transmitter above the line, and you'll notice that the horizontals are not horizontal, they are sloping. So that's the way to do it. It's not always possible to put your transmitter above the pipework. The strong recommendation is that you always do that, but if you cannot do that, look at the diagram on the left, ignore the fact that we've got horizontal pipe that should be sloping, and 5A and 5B are your isolation valves. Then you come down to some dropout pots of 7A and 7B. That just allows any condensate to be vented manually, or you can put an automatic vent on there. And then you come back up into your transmitter. That means you can avoid your transmitter getting full of condensate or any liquid that might collect in there. So long as the line between 5A and 5B, down line 4, and then back up to 3A, 2, and 1 is full of gas, you won't have a problem as long as your joints are good. And that 7A and 7B just allows you to vent the line. Same for liquids, but the other way up. So the preference is the drawing on the right. So your liquid is in that pipe work coming out and then down into the transmitter. Again, you can see all lines are sloping. You've got the 3-valve manifold there, which is indicated by item 2, 3A and 3B. And then you've got some drains of 7A and 7B. If the transmitter is above the active pressure taps, i.e. above your pipeline, then the drawing on the left can help you mitigate some of those issues. So again, this is for access for technicians, but be wary of installing like that. It's very easy for people to get these pipelines wrong, so look out for that. Impulse lines for vapors, i.e. steam, typically, again, you can come down, you can see that the lines should be at the same height. So on a horizontal line, that's much easier because you've got those 2 condensate pots in the left-hand drawing. On the right-hand drawing, those filling tees, it's difficult to show on the drawing that they must be at the same height, okay? And they should both be higher than the tapping on the pipework. That allows anything from those filling tees to drain back to the process, and they should be short, very short, because you've got steam in there that condenses in the filling tee. So just be careful if you're working on steam plant, read up on it, make sure you get that right. So yeah, we've got impulse lines for liquid and gas. That's just a line diagram, very much as we had, but this comes from the impulse line standard. So I'll pause again, Sunday. We're getting, how far through are we? We're at, I've only got a few more to go, but I can pause for a minute if you've got any questions on impulse lines, if you've seen any.
Yeah, thank you so much. Lincoln, you're doing very well. Any questions, please do place. And we are moving to very important bit now, the uncertainty of DP systems. This is very critical one. And I want everyone on the call to pay attention to this. This is where, especially here in my own country, people seem to neglect this aspect, the uncertainty. This is something very important, especially if you are buying gas or you are selling gas, natural gas or oil to a buyer or a seller. This part is very critical. It has something to do with your cost. So I will advise everyone to watch this part. Very important, and I really enjoy it. The fact that this is going back to basics, looking at the installation and effect of installation on errors. You can see this clearly. So I think you are doing quite well.
Great, thank you.
The questions that we have are those ones that we have treated before. If you're on this, if you are still here, please, if you want to speak, you can also raise your hand and we can allow you to speak. But for now, may I ask Mr. Lincoln to continue?
Yep. Okay. So a lot of the errors, the uncertainty that can come with differential pressure metering actually is in the slides I've covered. So that's impulse lines where you've got, and you'll see some of these in some of the examples that I've got, where it's not the transmitter, it's not the primary device that's the problem, it's the impulse lines. It's exceptionally common for that to be wrong, and it's exceptionally common for errors to occur within those impulse lines. So when you go on site, just have a look. I've got some examples coming up in a minute that will mitigate that, that you'll see. But this bit is fairly brief actually, because we're concentrating on the orifice plate side of things. But the secondary devices, what we've got or what we've covered on the installation is the pipe run, i.e. the inlet to your measurement point, the geometry of the pipe, the roughness, the fluid, the pressure, temperature, viscosity, composition if you've got mixed fluids. You know, you get differences in measurement if you use different steam tables, so that can happen, and your Reynolds number. Your secondary instrumentation, your differential pressure transmitters. So, and I'll talk a little bit more about these in a minute, but the accuracy of the differential pressure transmitter is everything. So if you look at that table there, you can see that at 100% flow, we've got 0.075 on a freshly calibrated transmitter if it's temperature controlled and in a nice stable environment. Now, as you come down the flow, so if you halve the flow, with differential pressure is a quarter. So let's say we've got 0 to 100 cubic meters an hour is giving you 100 millibar differential pressure. At 50 cubic meters an hour, you'll have 25 millibar differential pressure. And if you halve that again, so if we are now at 25% flow, 25 cubic meters an hour, that differential pressure is going to be a quarter of 25, which is 6.5 millibar. So at 25 cubic meters an hour, which is a quarter of the flow, we've got 16 of the generated differential pressure. And because most transmitters have an error of the calibrated span, and as you can see here, we've got 0.075% calibrated span, or it's just showing a poor internet connection, so hopefully you can still hear me and still see me. You can see we're starting to creep up that that error curve that's shown there. So, you know, and if you're looking at a 10-to-1 turn down, or even an 8-to-1 turn down on your measurement, so you want to go with a single transmitter from 100% down to about 15%, I think, to give you an 8-to-1 turn down. Your choice of pressure transmitter really becomes crucial. You can split the range, so you can have 2 lower cost differential pressure transmitters. And what you then do is you overlay 2 of those curves. You have one that's calibrated 0 to 100 millibar, that covers you from, say, 20% to 100% of your range. And you have another one that's calibrated, say, 0 to 6.5 millibar, or slightly over that. And that covers you from 25% of your range, perhaps down to 6% of your range. So that's giving you, I don't know, what's that, about an 18-to-1 turn down or something, depending on what your error is. But you need to pay attention to your differential pressure transmitters. They need to be stable, good quality, and look at that error. So if I just go on to the next slide here, the point here is transmitters have improved. The typical error in the 50s was 0.5% of full scale. If I go back to that original slide, so if we had 0.5% at 100% of our flow, 0.5% error, you can see that error curve would increase very, very quickly as we drop down to perhaps even 30% of flow. That was in the 50s. In the 2000s, or, you know, typically the error would be about 0.075% to 1% of full scale. And then from there onwards, development of high performance transmitters like the Schneider Electric S series, which has an of-reading error over a particular range, and I'll explain a bit about that in a minute. And you've also got the Emerson Ultra range, and these have been designed really for flow measurement. I shouldn't really miss the opportunity just to say, if you're looking at multivariable transmitters and flow computers, consider those, as the multivariables and flow computers will correct for all your changing discharge coefficients. That's your viscosity and your velocity that your one of the attendees asked about earlier. So transmitters are making a step change in the differential pressure metering industry, and the Schneider Electric S series now have an optional 0.025% of reading accuracy. That incorporates, so that's of reading, not the full scale. That means you get straight line error. Instead of that curve, it's a straight line down to about 25% flow, and then the curve starts to pick up. So you really increase the range of that transmitter, and you need to take the information digitally off that, not off a 4 to 20. But that now has a 0.025% of reading accuracy. So the accuracy is tighter at the beginning end. It's a straight line, not a curve. The way they've done that is they've incorporated 11 calibration curves in their firmware, and that will cover somewhere between 10-to-1, 30-to-1 turn down of the differential pressure before starting to incorporate an element of full scale component of that lower calibration curve. You can't see the calibration curves, they're embedded in the transmitter. So that's all temperature. So transmitters these days are temperature aged in an oven, and they calibrate those transmitters whilst they're going through their temperature cycle, so they get a characteristic of the sensor that then is incorporated into the firmware within the transmitter head. You can overwrite that, not overwrite, but you can override that by doing your own pressure calibration, but then that transmitter is going to be based on your reference accuracy and not the 11 calibration curves that are actually integral to the instrument. So it's important to keep that in mind. That allows you to improve performance. But if you just keep an eye on that curve, if you're using an instrument that has an error of full scale, this is the curve you'll see. If you want one that's of reading, you'll get a much better straight line error statement across the bottom. And then the other errors are the ones that we've discussed earlier, and they're not going to be the only ones. They're the common areas of influence on orifice plate metering. So, you know, attend to your transmitter performance. get a good quality transmitter, whoever's that might be. Make sure you get the best that you possibly can to install there. As I say, you know, people are bringing out of reading transmitters now, not the full scale, which actually are superior to the calibration standards that we take round as instrument techs to actually calibrate them. So these days you want to be verifying that the instrument is correct, not calibrating it. But just have that in mind, as it's important to be aware of. On flow computers themselves, you need to watch out for errors on programming the flow computers. It's not uncommon for the Orifice bore to be programmed in you know, a slip of the finger. Instead of it being 50.038 or something, you've got 50.308. So you can have the Orifice bore incorrectly programmed into the flow computer. That then introduces an error that is not the fault of the Orifice plate or the transmitter, but it's a data entry error. And this just happens when people are perhaps changing plates in and out. So that needs to be validated. Make sure you've got all that to hand. Venturis, typically, you know, there's a standard high pressure Venturi that we can use for wet gas. There's a one with a piezo ring installed, and flow's obviously going from right to left on that picture. There's, oh, you might not be able to see that. I hope you can. A typical installation that's been nicely installed using the impulse lines, which come down that what we call unistrut on the left and right hand side there, drop straight down to the bottom where we've got a dropout pot. And as you come back up, you can see we've got a low range and a high range. So we've got an extended range flow measurement off of that Venturi tube to give us a much greater turn down on the flow measurement side of things. Here we've got two multi-variables, so they're both doing the mass flow computation just with a single input discharge coefficient from the Venturi calibration. There's flow computers out now that will take a flow calibration that's got 19 points of discharge coefficient to velocity, therefore Reynolds number, and that flow computer can actually take 19 points straight into it and give you the temperature and pressure correction according to the gas laws and liquid applications. They come in some fair sizes, so that's a nice nice job there. Nice high pressure. You can see the size of the flanges there, so that's really good job to have got. But you can see the type of applications that we're doing, and we also do small Venturis. That's actually a Venturi nozzle that you can see there, and we go all the way up to some very large sizes. So I can't remember the size of those, but they were colossal on a mine. The architect unfortunately chopped the tops off all the Venturas that we were suggesting they had, and then compromised the inlet by putting a rain hat on it. So you need to be aware of what happens after you've supplied the equipment. So this is clearly that picture on the right, a compromised installation. You can also find ways to remove the impulse lines. So do lots of complex styles of orifice plate, and that orifice plate on the right that you see there, there's two impulse lines there, one running inside the other, and that means both those impulse lines are pretty much at the same temperature. And that's because, bear in mind, that fluid isn't moving, it's just static there. If it's out in the middle of the Sahara or something and you had direct heat on there, you might find there's a little difference between the impulse line that runs on the outside and the one on the inside, but you know, they're going to be pretty much the same. It's not going to take long for those to equalize. So that's a good way, if you can, to go compact to remove any impulse line problems. Here's an application. So again, you can see a compact orifice plate, again with a multi-variable, with that, that's on mine gas, so that is very, very wet. And it's 100% humid, so it's there's a methane, and the dropout pot next to it is just, it's like a tap running. I mean, it's all gas, but as it comes out the mine at 40 degrees and cools, all that moisture condenses out And so we replaced some thermal mass meters with the Orifice plate. The thermal mass meter just wouldn't measure it at all. The Orifice plate from day one went in and worked. So lots of different styles. Again here, we've got boiler feed water applications where the temperature of the fluid within that pipe is 90 degrees. But because the impulse lines are a dead end, that temperature cools very, very quickly. So that one's activation air. You can see in the distance there, in the middle of that picture, you've got two compressors left and right. They common up and then they go vertically up, and that's going into a water treatment plant for what's called that's going on to the I think they call it a RAS, rapid activation filter, RGF, rapid gravity filter. So what they do is they backflush the filters and they aerate it, and then they lift off all the sticks and stones and whatever that's on the top of the sand filter. That whirs over into and basically cleans the filter. I won't explain too much more about that. I've got a quick what's the problem here. You don't need to answer, I'll just talk about it. So here's a pitot tube in this case. It could be an Orifice plate, it could be a nozzle, could be anything. The question picture comes towards you and down the left-hand side. So you need, if you remember, we were talking about straight run of pipe. So we've got a pitot tube here installed virtually on a bend. So clearly that's a non-compliant installation. That's going to give you problems. Question is by how much? Well, for pitot tubes, there isn't any data. If it was an Orifice plate, we'd be able to work out and give some guidance on what the error is likely to be, but you can't really do that on this this application. So what else is wrong here? They've got a tapping just below. I think that's the main thing. It's fairly short inlet, double bend. We've got a bend in the distance and a bend in the foreground here, and then we're straight onto a pitot tube. Not a great installation. So that's a problem. But you can see we've got the transmitter closely coupled onto a manifold, so we don't have any impulse line problems here. Is purely the process pipe work. Let me do the next one. So sorry about the quality of the picture. What's the problem? So I'll slow down a bit, give you a second or two. And really the problem here is the quality of the pipe work. So this was measuring liquid. I couldn't capture the picture of the installation, but the transmitter is in that bottom right hand one, so it's an old transmitter. That impulse pipe work hasn't really been well serviced. It's quite battered. None of it was leaking, but it's in very, very poor condition. So you haven't really got any. Well, you do actually. There is a problem there, and that is it's a liquid application, and you can see the impulse pipe work as you come up to those vents at the top there. It then slopes back down again, so you've got the potential for lots of air to get trapped there. And how often they operate those vents to make sure they're purged is anyone's guess. So it was an old installation that they were using. They had problems. We basically suggest they replace all the impulse lines and renew everything, and put in a better maintenance regime to make sure that the air didn't collect at the top of those, the top of what is essentially the formation of a U-bend. This one wasn't too bad, and again, the quality of that image is very poor. But you've got a maintenance issue. It was a remote site, but you do have a transmitter that is installed at the top of a U-bend on a liquid application. Again, that we couldn't really mitigate that. There wasn't too much wrong with it other than everything was old and it all needed stripping out and reinstalling. It was blocked, essentially, was the big problem with that one. Now here's one that I will leave for you to ponder just for a second. Take a look at that, and I'm just going to give you a second to it to give you a clue. I'm going to start counting. So 1, 2, 3, 4, 5. There's another picture coming for that same installation. Just noticed I've got a poor internet connection, so I hope you're there. So I got to 5. I'll carry on counting. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Give you a second. 20, 21, 22, 23. So I've counted 23 joints on one of those impulse pipes in an installation that isn't very big. If you look at that, and there's something wrong with this as well, you know, you've got 23 joints on each impulse line, so that's 23, it's 46 joints, totally unnecessary. If you do swage lock, you could use one piece of tube virtually and get rid of probably something like 20 joints on each piece of pipe work. So customer says that there's no problem with this, but they do have a problem with the installation and it's not working properly. So we have instructed them to change that and make sure it's just instrument tubing, single piece, minimum number of joints. So you can bend most of that into place with a proper tube bender using swage lock or something. The other problem is the process is operating at 500 centigrade, and that 2-inch pipe mounting is welded straight onto the process pipe work that is at 500 centigrade. So I can just about hold or put my hand on that 5-valve manifold. It's hot, but I can touch it. So we're getting the transmitters heating up as well. So that's not protected or isolated from the process in a suitable manner. So we've got problems with that installation. We've got 46 pipe joints and a hot transmitter. So transmitter's got to be moved and we need to change out all that pipe work because it's just not good enough. And I'll let you just look at that as an installation. So these may not be methane-based applications, but you can see the problems that are easily relatable to any differential pressure metering installation. Here again, we've got a pitot. Number one, it's not straight, it's on air. And you can see we've got on that first bottom one on the right, first place water's going to collect is in that line, and you're not going to transmit the pressure from inside the process. So it's a problem. You know, that is just not going to work from day one, or it will work on day one maybe, but if as soon as you get condensation forming in that line, that's it, stops working. It's all over. So you need to take good and proper care of your impulse lines. That is the number one cause, I would say, of issues. Or certainly, if they're not installed correctly, it's going to bite you. It's not going to be a good installation. That one actually is fine. When you come out of a pitot tube or something, you've got to have a bit of horizontal, but immediately we have slope. If you look at the impulse line, it's all sloping all the way up to the transmitter. The only bit of horizontal is it just as it comes out that isolator. So got a temperature probe that it's okay. If that was on an Orifice plate, that would want to be further downstream. That's the red device, and the yellow device is the pressure transmitter. So it's okay for that type of installation. Compact Orifice for plates for steam, these are quite good. So you can compact mount the transmitter on a 240 centigrade steam line. It says DS3 there, but that's an RB30. You can see how these get installed. No impulse line problems there whatsoever. And that's pretty much brought us to the end. Where are we? 20 to 5. So apologies if I've overrun. There's a bibliography there. These are really important books to get. You've got the Flow Measurement Engineering Handbook by Richard Miller, and there's an ISBN number there. So grab a screenshot whilst that's there and get it. And you really must buy it. Other sources are, you've got Miller, you've got the Shell book, a few other things there. There's another source of information there called Orifice plates and Venturi tubes. That's Michael Reeder Harris. His ISBN number's there, so he is really like one of the flow gods, really, when it comes to Orifice plate metering. He's a really good engineer. Studied it at NEL for, I don't know, 20, 30, 40 years, something like that. I don't think he's retired, but if he hasn't retired yet, he will do soon. Excellent text that he's got, and for the first book I would get as the top one. Obviously you need the standard ISO 567, and there's 216, 2186 at the end, which is impulse lines, that gives you all those guides. Get the screenshot of that whilst it's on the screen. If you can't get hold of that, then Sunday I'm sure we'll forward you those ISBN numbers. But they're incredibly important texts that people use around the world today. And I think that wraps it up. I'm losing my voice now. Sunday, how was that?
Great. That was very good. Thank you so much, Lincoln, for great presentation. That was really good, very impressive. I feel like I'm back to school.
We're always learning. We never stop learning. That's the key.
Yeah. This is very good. This is very good. Back to basics. I'm sure everyone on the call has learned a lot. So very good lecture on the influencing factors in differential pressure metering installations. That was nothing short of brilliance. Thank you so much once again, Austin.
Thank you for the opportunity.
Yeah, we have two additional, at least actually 5 questions. So one of the questions was placed in the chat box. I will start with that one before we go to the Q&A part. If you want to say something, please do raise your hand and I will give you the floor to speak. Meanwhile, let's go through the questions, please. So Kelechi is asking, oh, sorry, Kingsley Ekechi is asking, can verification of orifice DP meter against clamp-on ultrasonic meter accurate than inspection of the orifice plates and primary instrumentation? I'm not sure if you get that.
Yeah, I've got it. Yep, I understand. So I've also got a lot of experience with ultrasonic metering, and we've done a lot with clamp and ultrasonics. If we're talking about gas, I wouldn't do it, full stop. Don't do it. If you're talking about liquids and you're trying to verify an orifice plate with liquids, it kind of feels like you need to define what area you are after. So you need absolute knowledge of the pipe work that you're clamping the clamp-on meter onto. You need a good ultrasonic as well, and even then you need to be careful because there are all sorts of factors that are embedded in the clamp-on ultrasonic that go to compute out the flow measurement. Now, they're good tools. We sell clamp-ons. I think they have their place in the market. If you're looking to validate an orifice plate to 0.5% or 0.7%, you're not going to do it with the clamp-on ultrasonic. That's not the tool. What you can do is verify that that ultrasonic, that orifice plate is working in and around the right order of measurement. So if the client says he's got a liquid application and he thinks the orifice plate is 30 or 40% out, you can use a clamp-on meter, and generally you'll be within 3 to 5%, something like that, depending on the pipe size. Okay, there's another caveat here. So pipe size. Ultrasonics are great on larger pipe, but as soon as the pipe starts getting smaller, you get more effects on them. And the manufacturers again try to mitigate that because they've made clamp-on ultrasonic meters for those of us that just need to pitch up, put the meter on and see if it works. There's all sorts of factors in that clamp-on ultrasonic meter that a lot of us aren't aware of. And there's many influencing factors that go to make up the resultant displayed flow rate on a clamp-on ultrasonic. So you can do it, but not to 0.5%. You ought to be thinking 3 to 5%. Doesn't matter whose ultrasonic it is. That's really where you should be using. And just make sure you've got a good ultrasonic as well, because there's lots of people making them now, and you just don't know what the engineering content is in some of those and where some of that data's come from. So be careful when you select your clamp and ultrasonic meter that you're going to use to verify your ultrasonic meter. Don't do it for gas. There's one or two that will do it for gas. You need high pressure, but generally I'd just be looking to use that for liquids. I don't think it's a great. It's not going to give you. It's not going to give you a precision-based validation, but it will give you an idea that the orifice plate is reading in the right area of measurement. 3 to 5%, I would suggest. It'd probably be tighter than that. It could be a couple of percent, but make sure it's a good ultrasonic. Always keep in mind, if you buy cheap, you buy twice. If that's a phrase you're familiar with. It's very true when it comes to ultrasonic. So there, you need to be careful with them. So I hope that's helpful as an answer.
Yeah, I think obviously that's very helpful. So you are saying that it's better to, because he asked two questions here. He asked, I mean, it's better to inspect the orifice and do all sort of maintenance on it than trying to verify its accuracy against ultrasonic, clamp on ultrasonic, right?
Correct. If you're using a clamp on, it's not going to validate your orifice plate. It's not going to do it. You need a full inspection if you're working to some tight performance figures. Let's say you're trying to work to like a 0.8% custody transfer figure. And all an ultrasonic's going to do is it's reading in the right sort of range. They're excellent meters if you get a good one. Their clamp and ultrasonic meters are excellent, but you don't validate your orifice plate installation with a clamp on. It's not good engineering practice. You can check it; it's reading in the right sort of area, but and really you're looking: is it 20% out, or is it 30% out? That can give you indication that the plate might be bent. But if you're once you get down to sort of 2, 3, 4% errors, your orifice plate, well, if they're different, it might tell you to actually investigate your orifice plate further. That's really what I would suggest.
That's good. This question is good because I have a client that have asked me to do this. They have an orifice on that measure gas going into a compressor, and they want to know how much gas is going to the compressor against how much gas is coming out of the compressor. So on installation, you have a DP meter. So they suspect that the DP meter is not reading rightly. So do you think that it would be a good idea to see the direction of the reading of the meter using a clamp on ultrasonic? Then from there, you now can advise the client to inspect the orifice meter.
Yeah, you can do that with gas. There's only one company that I'm aware of that will make a clamp and ultrasonic that will measure gas flow, which is a good one, which is important. But it's not a 5-minute job. It's going to take time to set up. You're going to need plenty of time to try and validate it. So I can talk to you about that one later.
I want to hear about that.
You've got right contacts, but just be careful. Yeah, just be careful, and it's going to take a bit of time to get right. So, yeah.
Good. I would like to hear that.
Yeah.
Well, that's a very good question and a good explanation. So for liquid, that wouldn't be a bad idea, right?
Yeah, not a bad idea.
And for large pipe diameter.
It's not a bad idea. Just be careful. Don't expect to get high accuracy. And I suppose, you know, accuracy is the wrong word. Uncertainty is the better phrase to use. It's going to give you an indication, but I wouldn't calibrate the orifice plate with an ultrasonic. I don't think it's the right tool. You need a proper inspection.
Good. Thank you so much. That was obviously helpful, and also thank you, Kingsley, for that question. That was a very good question. So let's go back to the Q&A chat. So Q&A chat, there's a question that's coming from Said. He said, do you recommend a regular footprint calibration of DP transmitter for a physical metering station, or the atmospheric calibration is enough?
Can you just repeat that again, Sunday? I missed a bit of that.
Is asking, do you recommend a regular footprint calibration of DP transmitters for a physical metering station, or the atmospheric calibration is enough?
Right, for fiscal.
So a footprint calibration,
Yep.
a full footprint calibration of a DP transmitter.
Yeah. So
or
footprint.
Atmospheric calibration is enough.
Yeah. So a footprint normally is when it comes in, you check it at atmospheric pressure. But if you're operating that fiscal system under full pressure, let's say, I don't know, you're at 10 bar, you probably want to do a 10 bar static pressure calibration of that orifice plate, of that differential pressure transmitter. Normally, excuse me, that means taking it off the fiscal installation, taking it to a lab. That's probably what I would do now. The fiscal side, I think Paul will be able to help you and me answer that question a bit more, but I think that would be a wiser choice, is to do full static pressure calibration on that differential pressure transmitter. That means pumping up to 10 bar, then applying your differential. That's what we do. That's the preferred method, because then your differential pressure, the pressure effect of the pressure effect on the 0 point of that transmitter has already been taken into account. So, and there is an effect on the full scale as well. So that's not something that was asked by your client, but that's what we would do and recommend, is make sure that calibration is done under the full line pressure of the installation. So take it off, send it to a lab, get them to pump it up to the operating pressure, and then do the calibration.
Yeah. Great. All right. Next question is, to what extent do drain holes in orifice plates affect measurement uncertainty, or is it negligible?
So drain holes, so long as they're done to the right size and the sizing is taken into account, and the sizing program takes drain holes into account, it's negligible. There is an effect, but it's low. That's a detailed question I'd need to check in more detail. But it's pretty negligible, generally speaking. It's and it depends on the size of the orifice plate and the size of the installation, but it's generally quite minimal, quite a minimal effect. The standard does cover that. I'd need to look that up. I think I might have it here. Perhaps Sunday we can answer that one on a separate email. If you're going to email everyone, perhaps we can look that up and we can get an email out to everyone to answer that in more detail.
Okay.
If that's okay.
Great. If you have any question, please put again in the Q&A, or you raise your hand, because we are getting close to the end of this. We have only a maximum of 5 minutes to shut this down. But if we don't have any question, it's going less than that. While we wait for a few questions, Again, just to go through some of the things that we offered. If you need any sort of training, metering training, we are more than happy to organize that for you. We have a couple of training on our website. If you can also check that. But generally, anything you think about metering in terms of training, in terms of services, consultancy, supplying equipment, we work very closely with many vendors. And again, don't forget that for our DP meters, DP transmitters, spare parts, DP Flow is strategically positioned to give you all the supplies for Daniel or the Daniel products. So maybe you, maybe I will allow Lincoln to talk about it. I know you concentrate on speaking on the technical side. You didn't mention it, you didn't say anything about some of the things that you have that are so interesting. Maybe I'll allow you to mention while we wait for some questions. Some
thank you.
They may want to understand what you offer as well. Thank you.
Yeah, thank you, Sunday. I really appreciate that. So we are offering a lot of spares. So I've got a couple of pictures here. So if I can just share my screen again, if that's okay.
Yes, do that.
There's the two.
Maybe after you share your screen, I would like you to comment on wet gas measurement, because I see in the field usually a couple of DP transmitters located where there is likely chance of having wet gas, and so I would like you to give some comment about wet gas measurement. And this sometimes also happens in even where you have custody transfer meters for gas.
Yeah.
So I would like you to give comment on that. How much to what effect does that have on certainty to both the seller, for the seller and for the buyer, generally for the measurement? But anyway,
Okay,
go through the spare part first.
Right. I'll just touch on spare parts. So let me just also, I think I've got a document open here. So yeah, here we go. So I'm sure you've got a lot of Daniel's installations, orifice plate installations where you are. So you'll probably be familiar with this sort of style of fitting. And
that's very common,
especially during COVID time. Yeah, there's been a lot of problems with supply of spare parts, and also these meters, they all look the same, but they're not. Even if you had the same part number, if they're made 1 or 2 years apart, they can vary enormously. And a lot of the castings were made, and then everything else was the casting was then machined to make everything fit. So you might think it's a standard product, but even 2 items next to each other on the same pipeline, on adjacent pipelines that perhaps installed a year apart, can be very different, even though they look exactly the same. So there's a couple of things that are incredibly important here, and that is make sure you've got historical data. Make sure you've got any reports, photographs, measurements that you can get, because what you think is a standard part might not be, and might be special. So as you can see here, this has come out of a Daniel's meter. It's quite a large one, as you can see. I mean, there's a trolley in the background there. You can see the size of the wheel. I can't remember the size on this. I think it's a 36-inch Daniel's. On this particular one, this has got a bonded seal, an elastomer seal that's bonded to the plate. Daniel's supply those, but the seal keeps coming off. So they've outsourced the supply of that bonding process. They've lost the side. So we can do these. Normally what we do is we start off by supplying a new plate with a new bonded seal, and then we can take the old plates back and bond new seals to them. To be fair, it's quite an expensive process, but it is achievable. In the whole scheme of things, it's probably better to get a new plate with a new seal. It's just much better control, less pain on site when you get there. To give you an idea of the spares that we're supplying, if you can have a look at this image here, you can see all the bits and pieces. You've got the clamp bar, you've got the clamping plate, you've got the gasket, you've got all the grease plugs, you know, you've got the handles that wind in and out the plates. I mean, and we've got these gear shafts here. We're supplying all these parts now from the original manufacturer. In Canada, we've got a warehouse with about $3 million worth of stock. So, you know, and bizarrely, you won't always find that the part you need is held within that stock. Quite odd, but it's an enormous amount of stock that we've got. We really need photographs, serial numbers, any data you can get, and we can normally turn some spares around for you in a fairly good time scale. So we've been getting reports of Daniel's getting quotes back in about 3 to 4 months. We're getting quotes back in about 4 to 6 weeks. So even though it's not as quick as I like, it's still very quick in comparison to some of the others. And we're not just doing Daniels, of course. We've got Canalta, FMC, Pico. So if you see any of these on site, do contact us. We'd love to, or contact Sunday, of course. Contact Sunday, and we're going to need data from you and get everything you can about that installation. Make sure you push the client to give you the reports that they've done historically, because you're going to need those to send to us so that we can get that spares item sorted. We're going to need all the Daniels part numbers, but Daniels part number alone doesn't define it. We've known this for some time, so you know, you need everything. So we do spares, and we're doing really well on that at the moment. So please let us know what you're missing. And so we can do the plates, and we can do all the seals, we can do the snap seals. Let me just see if I can find them quickly, if you can see that in the image there. We can do all the clamping bars, the clamping screws. These bars aren't standard either. It is ridiculous. So we've just taken an order and supplied 5 new clamping bars for a £1,500 senior fitting, and for these particular senior fittings, they were made differently. So we've now had to resupply another 5 bars that have a wider clamping bar because of the machining and the uniqueness of all these products. So keep it in mind. You really need to get data, and any measurements of the old equipment that you've taken out that we're replacing is also really, really important. But at the very least, send us what you've got. We can always send an email straight back to you saying we need this, this, and this. So, but at least we can start that dialogue going. Let me just see if I can find all. So here you go, all the snap seals and dual seals. There's all sorts of problems that Daniels have had with these. Some of them work brilliantly, and some of them don't work very well at all. Some people are having to crane the orifice plate out, which is an awful thing to do, but has to be done. Nevertheless, all those spares we should be able to help you with. New plates we can do, and the quality of them is very good as well. So just keep that in mind. We've just supplied new carrier plates to a particular client. What else we got? All those grease guns. Yeah, so I think that covers the spares. To give you an idea of the remit, let me just there we go. That's all right, I just can't quite see the menus there. To give you an idea of the remit, so we've got the flow meters, the primary devices, electrochemical, so PHRP conductivity, chromat, pigging. Here's the pneumatic pressure transmitters and the reading pressure transmitters. The website needs updating, but if you remember Sunday mentioning the fact that these work on a pneumatic principle. So these, instead of giving a 4 to 20 milliamp output, these give a 3 to 15 psi signal. Been around for donkey's years. They're not made anymore, and if you need them, please contact us. We can help you with them, with sourcing and supply. So that's the pneumatic transmitters. In terms of elements, we've got wedge meters, Venturis. We do single stage, multi-stage orifice plates for restrictions, pitot tubes, huge range of Venturis and Venturi nozzles. Oh, there's something I was going to mention as well, which you should talk to us about, is if you need any sizing software. That we do an engineering suite, it's a toolbox really, that does valve sizing for control valves, on-off valves, primary elements, thermowells, so for wake frequency testing, that's there. A lot of the old PTC coding now fails the more, or some of the original thermowells that were installed in flow measurement pipelines are now failing. So if you're trying to increase your throughput of gas in a particular application and you're retesting a thermowells, they're now failing a lot of the time. So that's something to bear in mind. You don't want a thermowell snapping off and going down a pipeline. So that software incorporates that as well. Very, very useful toolbox of engineering tools. Again, contact Sunday if that's of interest to you, and yeah, we can help you with that. The software is incredibly well developed and covers all the normal standards. So 5167 and the ASME codes are all in there for valves and flow and thermowells. It does have a level tool in there as well for measuring level with differential pressure transmitters. So that's in there. I think, Sunday, that's where we got to, wasn't it? I think that's yes, what you asked me to cover.
Yeah, there's a question here that a very good question that I would like you to talk about, which is Solomon is asking, can condensate ingress affect gas measurement, and how often can orifice plates be replaced?
Just let me just see if I can increase. Can't see the. Just read that one to me again for me.
You said that can condensate ingress affect gas measurement?
Yes. Yeah.
And then you say how often can orifice plates be replaced?
In terms of replacement, as often as you like, you can replace them every day if you want to, but that's not what he's asking. He might well be asking how often should they be replaced, and that all comes down to inspection. So the ISO 5167 standard tells you the condition of an orifice plate in order to be useful or to be used for measurement. If that plate on inspection falls short of those design limits, that's when you should replace it. Or if you are doing an inspection on day one, rather than take that to the lab and wait for it to come back, you should have another plate ready, and you just take one out that's going to go off and be inspected, and you put the new one in. That one you send off for inspection, if it passes, can sit in a box on the shelf till the following year, and then you just put that one back in, and then take out the one that's been in service for the preceding year and send that off for calibration. So you can do that. That's going to save you a lot of time on site, because you're just taking one out and putting one in. You can replace them as often as you like, but they do tend to last a long time unless you've got sand, unless you've got gas condensate in there. If you've got liquids traveling at high velocity down a gas line or sand, that's going to affect the upstream edge, and that's going to be a problem. So you tend to find orifice plates will wear on wet steam type applications, because steam will move at about 60 meters a second, whereas gas isn't moving as quick as that. I think it's probably moving at 20 or 30. So the momentum of those liquid particles isn't as high. A the effect of condensate within a liquid pipeline isn't so much the wear on the plate, in my view. Others may correct me on that. It's more the fact that you've got two-phase flow and you haven't got rid of the liquid before your measurement point. So if you've got two-phase flow, and it's a different presentation, and it needs probably a different engineer to go through that. But there are flow computers that will do that. There's all sorts of engineering tools that help you correct for wet gas. You need to take into account a Lockhart-Martinelli parameter and use some other equations for wet gas metering. So yes, condensate depends on the quantity, but if it is properly wet, I mean, by which you've got 3 to 5% liquid in your gas line, it's going to have a big effect. I can't remember which way it goes, to be honest. It's normally something I gin up on when I'm looking at a wet gas metering project. I can't remember whether under ease or over ease, but it does one or the other, and it's significant.
I just to support that, I read from somewhere when you have for orifice meter, when you have liquid, it overreads.
Yep.
Yes, it overreads. So basically, it tells you that you have gas flowing. The quantity of gas that the meter will read will be higher than the actual quantity of gas that is flowing in the pipe. So it's overread issues. Then there are some publications I've seen with you. There are equations that you can use that are used in correcting for overread. But I think as you say, that will be in a flow computer.
Yeah, it's not an easy one to do. So it's important to keep that in mind. It needs engineering properly, and of course it depends on the type of flood, the amount of liquid. Obviously, with an orifice plate, if it doesn't have a drain hole in it, it's going to start to dam up in front of the plate. So that's going to cause an effect. Plus, the force of the liquid going through the plate will create measurement errors. There's a whole load of things to take into account with wet gas applications. So it probably then is dependent on the amount of condensate that's actually within that pipeline would then affect the answer that we give that question. But yeah, it affects it in a big way depending on the quantity.
Great. So this one I'm reading now should be the final one because we are overboard already. So Oluwafemi is asking, can pressure fluctuation affect orifice plate, and what is the effect of particulate solid on orifice plate in situation where gas is not properly treated?
So pressure fluctuations will also then affect your velocity going through the orifice plate, and the ISO 5167 really is based on consistent slow changing flow rates. So I think the ASME standard expects transmitters to update 8 times a second or something like that. So when you're talking about slow changes, you are talking certainly in seconds in terms of changes. If you've got pressure pulsations, it's just not good for any metering installations. The reaction and response time of your pressure correction, your pressure transmitter is going to affect any meter on a gas line. Doesn't matter whether it's differential pressure, ultrasonic or turbine. A pressure pulsation is going to cause a problem with maintaining performance. So you don't want pressure pulsations in your pipeline. Also, they can damage pipeline equipment. So if you've got a turbine or a plate, depending on the pulsation, I mean, if it's a pressure shock, you can damage pipeline equipment. If it's a pulsation, like plus or minus 10% of the pressure, but it's changing rapidly, then your pressure and temperature correction devices aren't really going to keep up with that change. So that's not great. You need it to be fairly stable. if you've got particulates in there, let's say sand, for example, in your gas line, if your gas is moving quickly at 20, 30 meters a second, that's going to be like sandblasting the plate, and it's going to take off that sharp edge. That sharp edge is everything when it comes to metering. As you start to lose that sharp edge, you can start to get, a 0.5% error as where it would probably start at. That's going to mean you need to do regular inspections to check that plate. If you check that plate and it's in good condition, we can continue to use it. If you check that plate and you're starting to get abrasion of that sharp edge, you need to put a new plate in, or refinish the existing plate. You can refurbish an existing plate without too much of an issue. We do it. We've just been doing a few recently, when we just machine out that ding or that nick that's on the sharp edge. So you can refurbish a plate with a quality company. Machining a sharp edge on an Orifice plate is no easy feat. It's not just putting it on a lathe. You need a company that specialises in or if you have doubts, just replace the plate, put a new plate in. That's the key. Not from a local company that's machined it. They won't machine it properly. You need it from a company that specialises in Orifice plate metering. So that's sand and wet gas.
Good. Thank you so much, Lincoln, for your wonderful presentation. Excellent delivery. I think it was very engaging session, very brilliant questions. Thank you, participants, for your time to listen to this presentation. If you need any support with your metering, whether it's spare parts or it's new metering equipment or training, or you just want us to investigate issues with your metering or conduct a study to see your metering challenges, Fleissen & Company is more than happy to support that. We have a lot of consultants within Nigeria and outside to support you. We have a lot of so many OEMs to help. So to close, I would really want to thank you for coming, and of course thank Lincoln for his presentation. Thank you so much. Now we are shutting down, but I want to remind you of the conference that is coming up, the Nigeria Hydrocarbon Measurement Conference. Please do register to attend live in Abuja or virtually. Thank you so much. Bye from me. Bye, Austin.
Thank you, everyone. Thanks, Sunday. Really appreciate the opportunity.
Bye, everyone. Yes.
Take care.
Thank you.
Bye now.
Yeah, bye.